Okay, testing 1, 2, 3. Here is a beautiful, beautiful little function machine. Let me just show this up on the screen. Oh, look at that. And I got this new notation, f of x. So we talked about this recently, but I want us to kind of consolidate this a little bit more. And there's a couple different skills that we want to develop around this topic. So first of all, the topic is function notation, right? How do we notate functions mathematically, and what's that look like? And basically, what we're going to be using is a notation looks like this. This f of x, this f is the name of this function. This is the function called f. It's the function called f. And this function called f takes a single argument. And I know that it's a single argument because you can see right there, there's just one value that's getting passed to it. So if I want to call this function, I have to give it a value. And once I give it a value, this value is going to be placed everywhere in the definition of the function where that variable lands. So for example, let's say that my input to the function is x is equal to 4. Okay, if x is equal to 4, that means that this function is going to need a 4 that's placed in this x, right? Because that's the value that's getting passed into it. And then also, I'm going to need to place that everywhere that there's an x in the definition. There's just a single x that occurs in the definition. It's right here. So the substitution in would look like this. So you can see I'm now answering the question. Well, this is the function f of x. If I give it the number 4, what does it give me back? Well, you can see here's the expression, and now I just need to evaluate it. So the 4 goes in as the input, and then I replace the x's on the definition with those values. So a 4 lands here. Of course, 3 times 4 is 12. So I end up with 12 plus 5, and when I add those together, I get the number 17. So for this function, when I pass it 4, it gives me back 17. So f of 4 is the number 17. Let's look at another different input. So here is the same exact function, and you can see, but instead of giving it the value I gave it last time, we're going to give it a slightly different value. The value that we're going to give it this time is going to land in here for my input, and then every single place where there was an x, I'm going to substitute that out with the value that's getting passed into the function. And this time I'm going to use the value input x is 8. And you can see when I do that, right, the 8 lands here and here. The 3 times 8 is the 24. 24 plus the 5 is the 29. So 29 is the output. So I can say f of 8 is 29. And then if I'll look at one more input. I'll say my input this time is -2. And you can see that I'm placing the -2 here, symbolizing, hey, this is going to tell me what this function f equals when it gets a number -2. When it gets a -2 passed to it, this part becomes -6. And this is 5. And when I take -6 and add 5, I get -1. So I would say that f of -2, right, is -1. And I'm doing this twice. I don't know why. I don't need to do this twice. So I want to just kind of just summarize what we just looked at, right? This is my function definition. This current function is f of x is 3x plus 5. And the thing that I want to look at here is kind of a problem that goes a little bit in the opposite direction. So my question here is, okay, what value of x would force the value of this function to give me an output of 29? Say it another way. What x can be my input that would give me an output of 29? Right? In fact, let me write that down. What value of x would produce the output of 29? To answer that question, I might do the following. I might say, well, let's go ahead and write down 29. This is the target that I'm looking for, and I'm going to write that equal to the definition of this function, right? So if you look at this, what I'm saying here is find the value of x, right? This is an equation. I'm saying find the value of x such that 3 times this value of x plus 5 equals 29. Solving this is a pretty straightforward linear equation, right? I'm going to take away 5 from both sides. When I take away 5 from both the left and the right hand side, I have 24 equals 3x. And now if I divide both sides by 3, I'm going to get that 8 is x, or x is 8. So I can see here the value of 8. If I pass 8 into this function, it's going to produce an output of 29. Okay, so we can go back both ways, right? We can consider if I pass a function a number, it's going to give me a certain output, but also what number would I have to pass it to, in this case, what number x would I pass it such that it's going to force this function to equal 29? And you can see, to answer that question, I'm saying, look, I want to know the value of x that will make 3x plus 5 become 29. The answer is 8. And if I bring that 8 all the way back up here and I place it into this function, you can see, yeah, 3 times 8, 24, plus 5 is 29. All right, there's another little table here I want you to consider. It says determine the relationship between x and y in the table below and write the equation. Mm, mm, mm. Oh, there's something about these input numbers that I've noticed. So maybe you notice this too, right? There's something about this value 9. There's something about the value 1, 100, 4, 49. This is blank. 0, 25, and 20. And you can see there's some instances where we're given both value. I can see that if I put in 49, it becomes 7. I can also see if I put in 25, it becomes 5. If I put in 1, it becomes 1. All right, so listen, this is a very important thing to do. I want you to pause the video right now, and I want you to think about what function would produce this, and then fill in this table and write down the function rule. Pause it now. Okay, so now that you've had some time to think about it, right? I'm going to go ahead and talk about what I think the answer should be. Well, perhaps what the answer could be. So just looking at this 49 going to a 7, I know that if I take the square root of 49, I do get 7. And in a similar fashion, if I take the square root of 25, right, that would produce 5. If I take the square root of 1, that definitely would produce 1. So it looks like what I'm doing to my inputs is I'm taking the square root. If that's the case, that would mean this is 3, this would be 10. The square root of 4 would be 2. Now think about this. What do I take the square root of in order to get 4? That's kind of going backwards. And the answer here is 16, right? The square root of 16 would be 4. If I take the square root of 0, I would get 0. And the square root of 20, right, I can just write it like this. It's root 20. That's one way to write that for now. Also, if I wanted to write it in simplified radical form, that would be the square root of 4 times 5, right? 4 times 5 is 20. And I can rewrite this as the square root of 4 times the square root of 5. The square root of 4 is a 2, and the square root of 5 is not a perfect square, so I'd write it as root 5. So you could write it like this also, right? 2 times the square root of 5. If you compare that as a decimal to root 20, you're going to see that those are identical. So what we've got here is this function rule, right? If I'm given an input, what I want to do is I want to take the square root of that input, and that's going to produce this output. The next thing that I have here is a bunch of problems, and you can see it looks like I've got an answer already over there for C. But what I want you to do right now is I want you to ignore all of this, and I want you to go through and answer these questions. And let me just kind of give a little bit of guidance, because I definitely want you to pause this and do these before you check your work. But we're saying up here that you're given, for example, this very first one, this top one, you're given an input of, I want the laser pointer. You're given an input of -3. If -3 goes in here, what's the output? On the next one, you're given an input of 2. What would be the output? This one, the question is, what number would I put in there to get 125 out of it? -2 goes in, 2 goes in. What goes in to give me 99? And what goes in to give me negative 3? 4 goes in. What do I get out? Negative 4 goes in. What comes out of that? Okay, so pause the video right now. And I'm glad that you paused the video. I'm glad that you did those 9 exercises. If you didn't do them, pause the video. You're not learning anything if you're just watching me talk about this. You got to pause it and you got to engage in the struggle. It's about the struggle. All right, so now my assumption is that you did pause it and you did these exercises, and now we're just going to check work. So if I plug negative 3 into that first one, right, negative 3 is going to produce an output of 10, positive 10, because negative 3 times this negative 2 is going to be positive 6. 6 plus 4 is 10. On the next one, when I plug a 2 in there, this is going to become 7 to the second power, which is 49, and then I'm multiplying 49 times 3 and I get 147. This next one, oops, let me go back. This next one, I'm saying to myself, hey, what number, right, do I raise to the third power to get 125? And to be honest, I went through a couple. I've been down this road before, but I went through a couple energies. I tried 4 times 4 times 4, too small. So I just went up to 5 times 5 times 5. And yes, 5 times 5 is 25. And if you've got 5 of those 25s, it ends up being 125. So this, right, 5, 5, 5. 5 to the third power is 125. D is a little tricky, right? It turns out that if you take the square root of negative 1, right, that's not a real number. So the square root of, the square root of negative 2, you can't take the square root of a negative and still be in the real number system. So that doesn't have a definition under the reals, so we would say not possible. This one's nice. If I put a 2 in there, the numerator is going to become 5, and the denominator is going to become, let's see, 4 minus 5, which would be negative 1. So I got 5 over negative 1. So I could say f of 2 gives me negative 1. The next one over, I would say, I just added 1 to both sides. What squared gives me 100? 10 does. And it turns out actually, if you square negative 10, that's also 100. So this could be 10 or it could be negative 10. G is problematic also because you can't take the absolute value of something and get a negative number, right? We talked about this in class. The absolute value, right, would be how far something is from 0. So this is not doable. This next one, if I put 4 in for the x, I get 3 times 3 times 3 times 3. That ends up being the number 81, right? 3 is 9 times 3 is 27 times 3 is 81. So 81 divided by 2, right, is 81 over 2, or you can just write that it's 40.5. And then the last one, if I plug negative 4 in there, the absolute value of negative 4 becomes positive 4, and 4 minus 2 becomes 2. So those are those answers, right? And that's a nice nine question problem set. So I hope that you did those and you understand how those worked. There's one final thing I want to talk about before you start your review preview for the evening, and that's this. I want you to examine the function to find it right. So this is interesting. This function is being defined not by giving you the function rule, but I'm defining it by giving you its graph. So you can see here is the graph of the function. But this is a complete definition because it tells me, like, for example, if I put in negative 4, it looks like if x is negative 4, it looks like the function's hitting at negative 3. So when x is negative 4, you get negative 3. You see that? See how that works? Look at this. If I put in 2, it says I should get 5. Let's look. X is 0, x is 1, x is 2. So where is this crossing? So if x is 2 and I go up, it's just like, oh, it's right there at 5. You see? When x is, the input is 2, this function says 5, 5. It says, how about this? When the input is 1, what is the output of this function? Well, let's go look here. Here the input is 0. Here the input is 1. When the input is 1, it looks like the output is 1. That's amazing. 1 gives me 1. If 1 goes in, 1 comes out. If 2 goes in, 5 comes out. If negative 1 goes in, it looks like it's giving me negative 2. Negative 1 is giving me negative 2. If 0 goes in, it looks like it's giving me 1. Oh, you see, that's what B was. I was just looking for ones that had nice numbers. Yeah. Negative 1, negative 1, it's going to give me a value of negative 2. Right? When x is negative 1, y is sitting here at negative 2. One more down, it would be a negative 3, but you can see this is negative 2. So negative 1 gives me negative 2. 0 gives me, so again, I'm x values first. The x value is 0, that goes to 1. So 0, 1. Let's see, this says, what is the input of this function when the output is negative 2.5? Oh, well, to me, so the outputs are the y's, and I can see right here, here's negative 1 to negative 2.5, and I can see this function's hitting right there. You see that, right? Right where the dot is. So if I think about that, the question is, here is the output of 2.5, of negative 2.5. It's right there. The question is, what's the input that's going to give me that number? And you can see the input's going to be negative 1, negative 2, right there, right? And this function is called g. When g gets the number negative 2, right, then g gives back negative 2.5. Just like I could write this and I could say, hey, when g gets the number 1, g gives you back 1, right? If g gets a 1, it gives you back 1. So even though there's not a function rule here, you can see you can read this. You can read the xy pairs, right? You can read the x value and then the y value that's associated with it just by looking at this table. And finally, I just want to finish with the vocabulary that is in your book for today's lesson. And the vocabulary there is on angle relationships. So this is just some vocabulary, and I know most of you have heard these words before. It's nice to jot these down. If you find these are things that are unfamiliar to you, that's a really good reason to write them down in your notebook. If this is totally something you've known, like for many years, or if you've known for a while, don't worry about writing it down so much. But if two angles add up to 90 degrees, they have a special name. We call them complementary. Complementary angles have a sum of 90. Supplementary angles have a sum of 180 degrees, right? So if you look at this complementary pairs, this right here, you can see these are adjacent angles. There's angles that are right next to each other. And if I was to add this little angle with this little angle, right? If I was to add those two angles, I could call this angle, I can call this angle 1 and this angle 2. If I was to add, those two angles up, I don't know, my 1 keeps disappearing. If I was to add those two angles up, I get 90 degrees. And over here, if I add the 40 and the 50, you see I get 90 degrees also. Down here, these are adding up. This adds up to 180, so those angles are supplementary. These two are adjacent to each other. You can see that this angle plus this angle right here is making a straight line. So those two angles are supplementary. They add up to 180 degrees. The other vocabulary word there is vertical angles. Whenever we have two lines that intersect with each other, like the line that they give us, the angles that are across from each other are called vertical angles. So C and G in that diagram are vertical angles, but also angle F and angle D are also vertical angles, right? So they're the ones that are right across from each other are vertical angles. When a line called a transversal crosses two parallel lines, then the corresponding angles are equal. So here's some things, right? This is a corresponding angle, and this is a corresponding angle. They're in corresponding locations. And whenever the transversal, in this case, this transversal is L, when a transversal cuts through lines that are parallel to each other, those two angles are going to have the same number of degrees, right? And those are called corresponding angles. I know these lines are parallel from the diagram because of this marking. This marking right here, this little double arrow, is showing me that those two angles are, those two lines rather, are parallel, and those corresponding angles therefore are congruent. And then finally, when a transversal line L, you can see here's L again, when it crosses a pair of parallel lines, they're parallel, you can see because of these, you get a pair. You can get pairs of alternate interior angles. So in this case, they've highlighted angle F and angle M. Those are alternate interior angles, and they will be congruent to each other. They will be congruent when the lines are parallel. When the lines are parallel. If the lines are not parallel, but if they are parallel lines, those will be congruent. And also, H and G are also alternate interior angles, and H would be congruent to G also, right? They're going to be equal in measurement. They'll have the same number of degrees. All right, that's more than enough time. That's 21 minutes. You got about 20 minutes. Well, actually, if you paused the video right, this should be close to 30 minutes. I think if you paused it right. So it's time to go ahead and move on to the review and the preview. I look forward to seeing you again online and in classroom. This is Mr. Roberts. Talk to you later.